welcome to lecture series on advanced linear algebra. Today we will discuss about what is adjoint of a linear operators. We have already seen over a finite dimensional inner product space, if you consider any linear operator on it, its adjoints exist. But what about if the dimension of the space is not finite, what can you say about this issue? So, I will say that in general it may not exist also. So, let us define what is adjoint of a linear operator. Let V an inner product space IPS on a field capital F. It may be real or complex. Let T be a linear operator on V. We say T has adjoint provided there exists a linear operator T star on V such that for any alpha and beta belongs to V, inner product of T alpha beta equal to alpha T star beta. So, this is the definition of the adjoint operator. See, in the case of finite dimensionals, inner product space, this adjoint operator for every linear operator on it exists. I mean, if you define it, if you take a linear operator on capital V, which is an finite dimensional inner product space, then there exists a unique adjoint of the operator T. So, in this case, I mean in the case of finite dimensional space, the adjoint operator T star depends on inner product defined over your space V. So, if you change the inner product, then the adjoint operator will be also changed. Second things, if you consider for any order basis for B, say B, the matrix representation of T with respect to B and matrix representation of T star with respect to B, the relation between these two is not straightforward. Suppose this is equal to say A1 and this is equal to say A2, then the relation between A1 and A2 is not straightforward. However, if I consider orthonormal order basis, then we know how they are related. So, in that case A1 jk equal to A2 k j bar. So, this thing we have already seen. Let me consider a couple of examples in different spaces. So, let me consider first is let V equal to C n cross 1, that is space of all n cross 1 column vectors defined over the complex number C. Set of all n cross 1 column vectors defined over the complex number C. Consider an inner product defined by inner product of any x and y is equal to y star x, that is you take the transpose of y and then the conjugate. So, this is the definition of the inner product. Then define a linear operator T on V as follows. Was T of x equal to Ax, where A is n cross n fixed matrix defined over C. Then what about T star? I mean to say how the T star is defined over the space. Certainly T star will exist because V is finite dimensional inner product space. So, certainly T star will exist, but how T star is defined, that we have to see. We have, according to the definitions, for any x and y, T x y, inner product of T x and y equal to x T star y. Okay. So, this implies inner product of A x and y, which is equal to, according to the definition, y star A x, that is equal to T star y star x. So, we have to know what is T star. We have A x y, inner product A x y equal to your y star A x equal to, one can write down, this is A star y whole star and capital X. So, this implies that inner product of A x y equal to, according to star, this will be equal to x s star y. So, this implies T star, which is defined from V to V, is given by x goes to your S star x. So, this is the definition of the adjoint operator for this vector space when the space is equipped with this type of inner product. Now, let me just modify and second examples were basically similar to my first examples. So, let me consider, let V equal to C n cross n. I mean to say set of all n cross n matrix defined over the complex field C with inner product defined by, for any A and B, inner product of A B, because the element will be n cross n square matrix. So, this will be equal to, say, trace of B star A. So, this is my definition of the inner product for this space. So, consider a fixed matrix, say capital M belongs to B, then define a linear operator as follows: T of A equal to multiplying the fixed matrix M from the left hand side, MA. So, this is my definition of the linear operator T on V. Again, since the space is finite dimensional, so certainly you will have adjoint operator of T. Now, the question is how this adjoint operator is defined for this operator. Then what about T star? We have for any A and B belongs to V, inner product of T A and B equal to A T star B. So, this is the definition of the adjoint operator. So, let me define how this T star is defined over the V. So, this implies, left hand side implies inner product of MA and B, which is equal to B star MA. So, this can be written as B M star B whole star A. It can be written like this. So, this implies inner product of MAB equal to inner product of A M star B. So, this implies T star, which is defined from V to V, is given A goes to M star A. So, this is definition of the adjoint operator for this problem. Now, let me take an example over the infinite dimensional space and how to find the adjoint operator for that space. Let V be the space of all polynomials over C. I mean to say the coefficient of the polynomials are complex quantity. Consider an inner product on V as follows. For any F and G belongs to V. So, F and G both are the polynomials over the C. Inner product of F and G is given by 0 to 1 f of x g of x bar dx. So, the inner product is defined like this. Consider a linear operator T on V defined by T of G equal to F into G. I mean F is a polynomial and G is also a polynomial. here f is a fixed polynomial in V. I mean to say I picked off randomly one polynomial say f. The defining operator T on V as mapping T of G equal to f into G. Okay. So, now the question is what will be the corresponding T star? What about T star? We have inner product of Tg and H for any element H belongs to capital V and G belongs to the capital V. Inner product Tg and H equal to G T star H. So, we are looking for the adjoint operator T which satisfies these conditions. We are not saying that here T star will exist. If exist, then how this T star is defined? That we have to see it. If this means they have to satisfy this type of condition please. We have inner product of TGH equal to inner product of FG and H, and this is equal to 0 to 1 f of x, g of x, h of x bar and dx. So, inner product of Tg and H equal to like this. So, this implies inner product of Tg and H equal to, I can rewrite Gx and f bar x and hx whole bar dx. I can rewrite this one like this, so that without changing anything I am writing inner product Tg and H equal to like this. So, this is equal to, so this implies inner product of Tg and H equal to 0 to 1 Gx and dx, because f bar over bar means that is f itself. So, this is equal to inner product of G and we will have f bar and H according to definition of the inner product. So, this implies that this has to be equal to G T star H. So, this implies T star defined on V is mapping G to f bar G, G to f bar G. This is the definitions. So, here we have seen even though the space is infinite dimensional, but for a given linear operator like this we have found a adjoint operator of it. Now, let me slightly change the operators. So, space is same here, the inner product space is V which is space of polynomial functions over the complex number C and same inner product, and inner product is also defined by by the inner product of f and g equal to 0 to 1 fx gx dx. Now, let me define, let us consider the linear operator as D, that is differentiation operator on V. So, I have taken my linear operator's derivative. So, this implies that if I consider for any f and g, I will have inner product of dfg equal to 0 to 1 df by dx and gx by dx. Okay, let us consider g such that g equal to g bar. I mean, it is the coefficients of the polynomial g is real. Now, question is there any adjoint operator d star for above d? To answer these questions, let us proceed. What is the definition of star? We have inner product of dfg equal to 0 to 1 df by dx and gx dx. So, when I move with my integration of parts, this will be give me fx and gx 0 to 1 minus 0 to 1 fx and dg by dx dx. So, this implies that I will have f1 g1 minus f0 g0 minus 0 to 1 fx dg by dx dx. So, this is equal to this quantity minus it is your inner product of f and dg. Now, if you want to see that d star exists, if at all d star exists, then we must have dfg equal to f d star g. So, we must have in terms of the inner product of f and some operator operating on g, we must have this type of structures. Now, consider a functional phi on B defined by phi of f equal to f of 1 g of 1 minus f of 0 and g of 0. So, this is a linear functionals on V. Now, this linear functional is similar what we have already done over the same space. If you recall, why consider one linear functionals phi on that this type of space where phi of f equal to f of z naught, where z naught is a fixed value in your field say C, I mean complex number. So, in that case we have seen that for that linear functional there is no vector beta such that the linear functional can be expressed as the inner product of that fixed vectors. So, therefore, for this linear functional there is no fixed vector say h such that this will be equal to inner product of f and h. So, this implies that phi does not have, for phi there is no vector say H belongs to your V such that phi of f equal to inner product of f and H for all f belongs to V. So, this implies that D star will exist provided f of 1 g of 1 minus f of 0 and g of 0 equal to 0, and this is true for all function f. So, this implies that if this implies g of 1 equal to g of 0 equal to 0. So, if we choose a fixed function g such that g of 1 equal to 0 and g of 0 equal to 0, then we are getting the adjoint for the operator d. Otherwise, d does not have adjoint. So, now let me give some one interesting results about the adjoint operators in terms of the small theorems. Let V be a finite dimensional inner product space. Let T and U be any two linear operators on V, and C belongs to the field capital F on which the vector space is defined. So, let V be the finite dimensional inner product space. Here I have taken the vector space is defined over the field capital F. It may be complex number, it may be real number. Let T and U be any two linear operator on V and C belongs to the capital F. Then adjoint of T plus U star, adjoint of T plus U star equal to adjoint of T star plus adjoint of U star. Second, adjoint of any constant C multiplied to T will be equal to C bar and T star. Third, adjoint of T and U star will be equal to adjoint of U multiplied to adjoint of T. And the fourth one, adjoint of adjoint equal to T. So, this proof is very simple. I will prove one or two, then we will leave it on you and you can take it as home assignment to cross check the result please. We have for first, we have T plus U operating on alpha. If I take the inner product of this one with beta for any alpha beta belongs to V, T plus U inner product of T plus U operating on alpha and beta is equal to T of alpha plus U of alpha and beta. So, this is equal to T alpha beta plus U alpha beta. Since T star and U star exist, so this will be equal to, I will write down alpha T star beta plus alpha U star beta. So, this is equal to alpha T star plus U star of beta. So, this implies that adjoint of T plus U will be equal to adjoint of T star plus adjoint of U star. Exactly same way we can prove all the rest of the uh, results. So, you can complete in your home. One nice property of this adjoint operator is like this. Consider T be a linear operator on a finite dimensional inner product space V. Let T star be its adjoint, T star be its adjoint. So, one can write down T equal to T plus T star by 2 plus I times 1 by 2 I and T minus T star. So, one can write down T equal to like this. So, this implies that it is something like U1 plus I times U2. Here, what about the adjoint of U1 or adjoint of U2? Here U1 star equal to T plus T star by 2 star. This will be equal to your T star plus T star star. So, that is equal to by 2, which is equal to T star plus T by 2, and this is also equal to T plus T star by 2. This is equal to U1. And similarly U2 star is equal to U2, U2 star equal to U2. An operator T on V is said to be self adjoint provided T equal to T star. So, from this above relations, I mean T can be written as U1 plus I U2, where both U1 and U2 are self adjoint. But I am not saying that the operator T is self adjoint, but if you give me any linear operator on a finite dimensional inner product space, I will be able to express as a sum of two self adjoint operators following the complex number pattern, that U1 plus I is basically root over minus 1. So, U1 plus I U2. One may also raise the question, what is the beauty on it? Later on I will show you that if a operator is a self adjoint, then the corresponding space will have an orthogonal order basis. So, this orthogonal or orthonormal order basis will certainly simplify the structure of the operator. To understand the operator very easily, this type of existence of orthonormal order basis is useful. We will discuss in our future classes.